Então, bom dia, é um prazer estar aqui para apresentar o professor Mark Ablowitz, né, da Universidade de Colorado, em Boulder. E aí eu fui fazer um deverzinho de casa, vocês veem quantidade de folhas, eu não vou falar por muito tempo, claro, para não tomar tempo da palestra, mas quantidade de informação que eu preciso aqui usar um cardápiozinho de coisas para apresentar o professor Mark Ablowitz, que trabalha em ondas. Ele vai falar sobre ondas aquáticas, ondas no oceano, ondas óticas, problemas ligados à comunicação, fibras óticas e outras coisas mais. Então, uma série de trabalhos em pesquisa, artigos, livros, inclusive, sempre no curso que eu estou dando agora de variáveis complexas, fazer propaganda de um lindo livro recente, do final da década de 90, em variáveis complexas aplicadas com focas, livros em espalhamento inverso, no qual o professor Ablowitz teve um trabalho fundamental, junto com colaboradores. Inclusive, eu também fazendo meu dever de casa, é impressionante, vocês entram no Google, veem as citações do livro em Solitons, Nonlinear Equations, 1.300 praticamente citações no livro do professor Ablowitz. Isso já fala da importância desse trabalho na solução de equações diferenciais parciais não lineares ligadas a ondas. E aí, no meu dever de casa, tem que ver aqui, porque é um prêmio recente, o professor Ablowitz, com uma lista de distinções. Recentemente, agora em 2006, teve também a distinção de Professor of Distinction do College of Arts and Sciences da Universidade de Boulder, Colorado. E na página que eu visitei da Universidade de Colorado, tem a frase que diz o que precisa ser dito, que é for the exceptional service in teaching and research or creative work. That's in the page of the. It's not my words. It's the University of Colorado's words. So what can we do? E então é um enorme prazer apresentar o professor Ablowitz com inúmeros papers em ondas, todos muito interessantes. E então, nada melhor que então deixar o professor Ablowitz. So now I will speak in English so I can say the title. It's really a great pleasure that you're here visiting us and also giving another very interesting talk on Monday in our workshop of PDEs on dispersive shock waves, right? So today the title of the talk is Solitons, Discovery, Impact, and Applications. Thank you very much.
Thank you very much, Andre. It's been my pleasure to visit. It's my third trip to Rio de Janeiro. The previous two were in the early 1980s. I'm happy to meet my colleagues again, Andre Nachman, George Zubelli, Carlos Tumai, and I also have a colleague in Brasilia, Ketty Tenenblatt, who I worked with. And I understand she might have been or was the president of the Brazilian Mathematics Society. I saw her a couple of years ago in Colorado. I was very interested to see all the students here, and it's wonderful. And I noticed the beautiful T-shirts outside, so I couldn't resist, and I bought one. And so I'm going to give this lecture in Brazilian design T-shirt. Very nice. And it says, math is, you can read it. And this lecture, I hope, will be, partly, math is fun and waves are fun. I hope. Let me get this. Yeah. Is that okay? Okay. So, let me tell you about today's lecture, which is going to be very basic and elementary, actually. But hopefully, again, will be something that you'll enjoy, as I enjoy it. So the outline, history, where did solitons come from? They just didn't pop up in somebody's mind. It's a physical phenomenon. One of the key ideas underlying solitons is the so-called inverse scattering transform, and I'm going to boil that down to just the method without the theorems, they can be found in the books. Impact. Turns out solitons have substantial impact. Applications, and I'll cover a number of these. Certainly water waves. Andre and I love water waves. Onde. Did you say ondes? Onde. Internal waves. Very interesting. Optics. I should tell you something about communications. Maybe I'll have time for lattice waves, probably not. And then pure mathematics, really, just waves with zeros and ones. And conclusion. I couldn't give this lecture without going back to Hokusai, great Japanese artist, and his famous wave, great wave off of Kanagawa in the early 1800s. But this lecture really begins with a discussion of Scott Russell. Scott Russell was a great fluid dynamicist, lived in the 1800s, 1808 to 1882. He actually died completely poverty-stricken. He discovered something, and he spoke about it in his report on waves, 14th meeting of the British Association for the Advancement of Science in 1844. His discovery was 1834, and I'll just read his statement, which is very remarkable. This is in 1844 when he wrote it. I was observing the motion of a boat drawn along a narrow channel by a pair of horses. The boat stopped, but the mass of water accumulated around the front prow. It rolled forward with great velocity, assuming the form of a large solitary elevation, a rounded, smooth, well-defined heap of water which continued its course without change of form or diminution of speed. He followed it on horseback, rolling on some 8 or 9 miles an hour, preserving its original figure, and after a chase of 1 or 2 miles, he lost it in the channel in the month August 1834. You can calculate. This is August 1st, so go back. How many years is that? This is his first chance interview with that singular and beautiful phenomenon. Well, they tried to recreate it in 1983, but couldn't. In 1995, they recreated it just outside Edinburgh, on a little channel, aqueduct, over a road. Now, why? They took a boat, you see that boat? And they sent it down that channel, and then they stopped the boat. This is what happened in 1834. But it was on the whole canal. So when they tried to reconstruct it, they only had that little boat in this big canal, and it didn't do the job. But now you see what happened is the boat stopped, and there sent forward a little hump. And that's what he saw. He saw it, and he followed it for a few miles. And he did experiments, and these are a figure from his original experiments, and there you have a solitary wave. Very easy to reconstruct a solitary wave in water. He was able to do it, and he even had interactions. You see these guys interacting. I'll talk about that. And he said to mathematicians, of course, he was actually a naval architect. He said to mathematicians, it was not supposed to be that after its existence had been discovered, phenomena determined, endeavors would not be made to reconcile it with existing theory, or to show how it ought to have been predicted from the known equations of fluid motion. Said differently, it remained for the mathematician to predict the discovery after it happened. Well, that's a lot of what we do. There's nothing wrong with that. Physicists see something, they tell their friends in mathematics what's going on, and in fact, my lecture on Monday will be exactly that. Because they really want to understand more deeply what they see, not just get data. Of course, if they have to just get data, they get it. So he said this, and there was a great fluid dynamicist at the time, Airy, and he said, no way. all waves break. No, you didn't see it. Of course, he saw it. He did experiments. But Airy was a pretty well-known mathematician, so that didn't go over. But in 1871, Boussinesq, in a tome, a huge paper, understood where this equation, the right equations were, so to speak, a simpler equation. So a lot of what applied mathematics is about, getting a good model. If you don't have a good model, what can you prove from it? You can't prove anything. Boussinesq understood that shallow water waves was a simplicity, it was a reduction from the original equations. And then Korteweg and de Vries spent their whole time in 1895 to describe small amplitude, long, or if you will, shallow water waves. And in the paper of Korteweg and de Vries in 1895, they write this equation. Eta is the height of the wave from the undisturbed depth. That's the unknown. The eta sub t and eta sub x are partial derivatives. And h is the mean height. G is gravity. T is surface tension. Most, in water, surface tension can be taken to be zero, essentially. But in other applications, when you don't have different fluids, you don't take surface tension zero. So this was their original equation, and it's third order. If you rescale it, what we often like to do when we calculate is to rescale, normalize the equation so you have units of 1. It's easier to calculate. This is the equation you get. So U is related to the amplitude, eta. And this is the Korteweg-de Vries equation. UT, UUX has this convective term and a third order derivative. Well, that equation was derived in 1895. And Korteweg and de Vries, and in fact Boussinesq, who wrote down this equation in various forms, knew there was a special solution. Hyperbolic secant squared, kx minus 4 kappa squared t. So the amplitude of hyperbolic secant has main at 0 when this argument is 0. Magnitude is 1, so the amplitude is 2 kappa squared, and the speed is 4 kappa squared. So the speed and the amplitude relate, and that's exactly what Scott Russell observed and wrote in 1844. And this is a picture of that wave at t0 and x equals 0. That's the mathematical, that's bringing it down to its rudimentary form. And here, now you're not in just any place, you're in Rio de Janeiro. I mean, if you're in the middle of the United States, in the middle of Brazil, it's one thing. But you can go to Copacabana Beach. And you can visit Marcio, a dear friend of mine who was an undergraduate of mine, actually, at the University of Colorado. And he lives very close to this magnificent beach, Copacabana. And you can look for those waves. Now notice the difference between a wave here, which is breaking, and you got turbulence and whatnot, and this long stretch, this one-dimensional wave. That's really where you get it. This actually came from Hawaii. I'm sorry, but I wasn't visiting Rio. And you even have surfers, and you got everything. I mean, how can you do better? How can you like any other subject but waves, right? From 1895 to 1960, basically, the Korteweg-de Vries equation were known to fluid dynamicists who did water waves. It wasn't any other application. But in 1960 and on, mathematicians developed very effective perturbation methods, and it became clear that the Korteweg-de Vries equation arises in very wide generality. Whenever you have weak dispersion or weak nonlinearity, you get the Korteweg-de Vries equation. So it doesn't just come up in water waves. It comes up in plasma physics. It comes up in lattice dynamics. It comes up in internal waves. And those are some of the internal waves is another subject I'll mention later. But in 1965, solitons were first observed numerically. Very remarkable. 1965 was not a time when you had a computer like this. 1965, you had to write a code. You had to put it on cards, as I did, goes to somebody to run it. And you got to be lucky your priority wasn't so low that it never got run. And they saw these solitons numerically. They saw these waves, these hump-like waves. In 1967, a method to solve the Korteweg-de Vries equation. Let me go back and say something about the Korteweg-de Vries equation. This is a third-order equation. Mathematicians primarily had been interested in second-order equations. So this had two things. It was nonlinear, and it's third order. So mathematicians really didn't spend that much time studying its properties. Almost no time. So, method to solve or to find the solution. What I mean by method is it's a linearization. The linearization of the Korteweg-de Vries equation in its skeleton form was presented by Gardner, Green, Kreskel, and Muir. And it took people a few years to absorb what was being said. In the 70s and 80s, the method was extended to many systems in 1+1 and 2+1 dimensions and discrete problems. I don't have 3+1, but if anybody has an idea on how to solve 3+1, let me know. It's open. And the method which really emanated is called the inverse scattering transform, and I'll give you the skeleton of the idea. Fourier analysis for nonlinear problems is very similar to that. And we wrote a few books. This was the earliest one. And as you go from book to book, at least in ours, you'll see how our thinking changed and how the method gets refined. But it takes a lot. It's a substantial amount of mathematics. One other thing, you can linearize not just PDEs, but ODEs. And these ODEs, which I'm not going to have time to talk about in this lecture, go back to great French mathematicians at the turn of the last century. Painlevé, his student, Chassis, and remarkably enough, there's a direct relationship between Chassis' equations and equations written down by Ramanujan, strangely enough. So if anybody is interested, they can see that reference in 2003 with Chakravarty and Halberd. But today I'm talking about solitons. I'm going to just say a few words about inverse scattering transform. The next slide's a little bit of the background to this method. So what you do is you take a nonlinear equation, the equation we're interested in, say, is the Korteweg-de Vries equation, and you make it, you find associated with it a compatible system. Psi is an auxiliary function. If you know u, then this is a linear equation for psi, and so is this. The problem is, how do you find u? All I'm telling you here is there's a compatible system. And compatible means if you take the time derivative here and 2x derivatives here, you will find that this equation, Korteweg-de Vries equation, is satisfied as long as k, this parameter called isospectral flow, because this parameter is an eigenvalue, is what we call isospectral, doesn't evolve. Now this equation is just not any old equation. We've seen that before. That is the time-independent Schrödinger equation. Well, there's time here. I meant that usually in the Schrödinger operator, you have a d psi dt. Here, time is a parameter. Well, physicists had studied it. Mathematicians had studied it. And there'd been some very important work. And when people realized that they had, in not quite this form, but in related form, Gardner, Green, Kreskel, and Muir, realized that this equation was around, they understood from that work that had been done heavily in Russia at the time, that they could develop a method of solution. Before I tell you that method, let me tell you a few paradigm equations that also have compatible linear systems and are solvable by inverse scattering and transform. Perhaps the most famous is the nonlinear Schrodinger equation, both scalar and vector. You could be a vector. This equation is solvable. Sine-Gordon equation, the three-wave interaction equation, 1, 2, 3 cyclic, a two-dimensional form of the KdV equation called Kadamsev-Pefiashvili, a singular integral equation where you have a Hilbert transform, and discrete equations. Call this the integral discrete equation. So all of these and many others, hierarchies of these equations, are solvable. What's the elements of the method? Well, the first step is to associate a nonlinear equation with this compatible linear system with a parameter k. So for the Korteweg-de Vries equation, this is the key compatible system, and you look at this one first. And that, what you do is you have a direct problem. You give me initial conditions. For a PDE, you give initial conditions, and I outline it for what's called decaying data. And you transform the initial conditions to scattering data. If you've ever solved a problem by Fourier transforms, and I'm lucky to teach an undergraduate course in the fall on Fourier series boundary value problems, well, what are the things you do? You transform initial data to Fourier data. Here you transform it to scattering data. And in KdV, it corresponds to what's called the reflection coefficient, discrete eigenvalues, and norming constants. Discrete eigenvalue means that the eigenfunction is in L2. You then use the second compatible equation to find the evolution of the data, and then comes what's called the inverse problem, sort of the element of inverse scattering. You use inverse scattering to recover from S the eigenfunctions, and from the eigenfunctions you can get the solution. You can also do long-time asymptotics. We did that back in the 70s, and a more powerful method was developed, steepest descent methods, by Deift and Zhu and collaborators. So they developed it for other problems. But they also recovered the asymptotics we found, which we used WKB methods in those days. And as I said, it's similar in spirit to Fourier analysis. Just a word more detail. Actually, this problem, the difference between inverse scattering transform and Fourier analysis is, Fourier analysis, you have integrals. So you're investigating the property and the regularity of integrals. In inverse scattering transform, you're investigating linear integral equations. You have to find the space of functions for which you can map the data to good scattering data. Good scattering data is data that you can invert. In KdV, the function class is what we call L11. It's a weighted space. Decay is faster, slightly faster than L1. So you map the initial conditions to eigenfunctions and find analytic functions. You find that these analytic functions remain, the analytic data is evolved correctly. You can then develop, leading from the direct problem, an inverse problem, which we call a generalized Riemann-Hilbert problem. G of k contains all the information about the scattering data. From G, you recover psi plus and psi minus, and this has the eigenfunctions and U in it. To go beyond this really would get me beyond a colloquium lecture, so I won't say much more except that for all of these problems, whoops, go back here, for these equations, the nonlinear Schrodinger equation, the Sine-Gordon equation, three-wave, 2 plus 1, class of 2 plus 1 problems, singular integral equations, and the discrete equations, you can do virtually everything I'm saying. Maybe for one or two of them, there's a little gap, but for the bulk of them, you can give precise function classes for which you can map the data to the direct problem and then recover it in the inverse problem. Now, let's go back to the quadratic de Vries equation. I said part of the scattering data were eigenvalues. They correspond to L2 eigenfunctions. Well, if you take one hyperbolic secant squared function, put it in as initially, t equals 0, then you will recover this guy from that machine I told you about. Suppose you took two of them, two hyperbolic secants. Well, this one moves faster than this one. Big guys move faster than little guys. They're going to interact. And this is what Kreskel and Zabusky saw in 1965, and then came out of this inverse scattering transform. You interact them. Well, they interact, and the big guy comes out, the little guy comes out with exactly the same amplitude and speed that they came in first. They call that soliton. That was it. That's what it came out. And that's the way the field found, if you will, solitons. And all those equations that I listed have this property, that they have waves, and when you interact them, they are elastic interactions. The big one comes out with the same amplitude as it started, and the little guy, same thing. And these correspond to discrete eigenvalues of the linear scattering problem. Well, we're talking 2007. I'm telling you about work in the 70s, and when I started doing research in this field, a soliton meant an elastic interaction. That is no longer the case. And you just give up. You just redefine your terminology, that's all. Meaning, to me today, a soliton is a solitary wave. Exactly what Scott Russell called a solitary wave has been renamed a soliton. I don't know why. People like the word. They like it better than solitary wave. I'm all for it. A solitary wave is a hump, a special solution of a nonlinear partial differential equation. That's what it is today. An elastic soliton is the one I'm really telling you got developed first and is related to the machine of inverse scattering transform. I don't want to confuse anybody, because every time I give a lecture and somebody says, well, soliton is elastic. No way. Soliton is almost anything these days, as I will now tell you about. So today, researchers use solitons to denote solitary wave. Some fields, I talked about water waves, coastal engineering, internal waves, optical communications, plasma physics, Bose-Einstein, biology, you name it, pure and applied math, solitons are there. If you go, we're living in 2007, that is, you go to Wikipedia, defined. It's really a localized wave. They don't really get into the interaction too much. If you go to Google Scholar, this is the up level, Google, you see 170,000 results. That means it references a body of work. If you go to standard Google, at least a couple of days I did, it went to 3.2 million. That's a little bit more than just science. Somehow this word has moved into the popular literature, so let me tell you about that. If you like art, well, this is really what they call soliton art. Many Faces of Solitons by Takasaki, Koto University. He has graphical solutions of interactions. If you like that, you got it. And he tells you how to solve the equations. He has codes for you. If you like bicycling, for some reason, there's a Team Soliton at Warp Speed in Vancouver. And if you like designs and vision systems, you will like Soliton Technologies out of India. They say on their website, every person in the company is a soliton. And they say further, like the soliton, wave is indestructible and everlasting within the company. Guaranteed that's not the United States. Nobody is lasting. And if you are into Star Trek, this is your thing. Season 5, Episode 10, you can see the USS Enterprise participating in a new propulsion method called the Soliton Wave, which my son tells me means there's infinite energy out there. Or at least energy isn't properly conserved. Now, word about asymptotics. When we studied general initial conditions from inverse scattering, we found that it emanated solitons, which moved to the front, and a wiggly train behind. That wiggly train led us to understand it, and it turns out to be related to a self-similar solution. The Korteweg-de Vries equation, if you make this transformation, x over t to the third, in a certain region, x over t to the third equals order 1, gets you into this third order ODE, which by a transformation of variables led us to the second order equation. So back in the 70s, when we were studying this problem, we had this equation. We said, what a nice equation this is. Get rid of the w cubed, and this is Airy's equation. So we said, oh man, Airy's equation is nonlinear Airy. And we realized it had been studied, anything that's pretty has been studied, by French mathematicians, in particular Painlevé. This is the second Painlevé equation. There's 6 of them. So we used asymptotics to get a so-called connection formula between the properties at one end and the other. We could connect this guy to the wiggles here, which is a nonlinear version of Airy's connection formulas. But this equation has very important properties in the complex plane. If you pick any ODE out of the bucket, second order, write it down, nonlinear, it will not have nice properties in the complex plane. Nice means it's meromorphic solution. Meromorphic, only poles. Most solutions you pull out have branch points, which lead to branch cuts, which leads to a lot more complication. So all these equations are special, and in those days, you talked about Painlevé and people thought you were talking about the moon. Painlevé was not a common term, but as you watched over the years, because of its beautiful mathematics properties, it led to a lot of work, and today it's a whole field of study. You can see earlier discussions, 81, 91 in our books, but there's a whole, there are books on Painlevé equations. I'm not going to say much more about that. There's the two-dimensional version of Korteweg-de Vries. You see Korteweg-de Vries here? Right there. Now, if you take d dx and add on two y derivatives, that takes curvature into account, slow curvature. If you remember that water wave, you had that front, and there was that nice smooth curve. That's the kind of structures that the KP equation describes. It's named after Kadamsev, Pefiashvili, and they derived it in 1970 from water wave, in plasma physics. We did it in water waves a few years later. It was the first 2+1 system that really can be analyzed by inverse scattering transform. So that machine I told you about applies. And you have Riemann-Hilbert, and also another sign, depends on the sign. Whether this is 1 or -1, your inverse scattering changes. Either it's a Riemann-Hilbert problem or something more, somewhat more complex called the D-bar problem. But interestingly, there are lump-type solutions. And let me show you a solution. Here is a rational solution decaying like 1 over x squared or 1 over y squared or 1 over r squared to this equation. X prime is x minus cxt, y prime is y minus cyt. And cx, the velocity, is positive in the x direction. Kr and ki relate to these eigenvalues. For various reasons, we're interested in optics, especially in classes of multidimensional problems that have decaying solutions. So we developed a numerical method to obtain things like this. So this one is a good check. And it looks like that. I don't know how well this is in the Y direction, it decays, and in the X direction, it's a little dimple. And this comes out of water waves with strong surface tension. It's not been observed yet. And the problem is with strong surface tension, it's hard to deal with fluids. So only the Korteweg de Vries equation with strong surface tension, only recently, 2 years ago, was observed in real fluids. Here is a solution to the Kampf-Darmstadt-Pfeffi-Feli for one of those choices of sign when the surface tension is small, actually. And that's a numerical solution. And this is a photograph off the coast of Oregon. And we like to say that's a KP type solution. We like to say it. Looks pretty good. Here's some more exotic solutions that people have found recently in 2005, 2006. These are exact solutions of the KP equation. I mean, that's a spider web. It's fantastic. I mean, it's hard to believe they find such solutions. Now, let me tell you a story about internal waves. Now comes mostly snapshots of applications. They were drilling for oil in the 70s off the coast of Indonesia. And they had a big oil rig, Exxon. It's 1970s, just like today. And every 11 hours and something, the oil rig, this huge oil rig, is turned around twice, 720 degrees. And then it goes away, and calm prevails. So they wanted to understand what was going on. And that turned out to be related to internal waves, waves that move in the internal part of the ocean. These are what we call waves that move along the thermocline. Thermocline is where the density changes rapidly. Temperature changes, temperature and density are related. And you can derive either KdV when the waves are very long, or if the depth is very, very deep, you can also get the Benjamin-Ono equation I mentioned earlier. Both these have solitons. So at any rate, they got some photographs from NASA, and they saw in the location of this area where they were drilling these striations. And here's some snapshots from the platform. You don't see much here, but you see right up there some waves. Okay? And then the waves come, and then it gets choppy, and then you get about 6 to 8 foot waves on the surface. The choppiness goes down, 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 and then flat. What's going on? Well, Osborne and Birch said, this is giant solitons, internal wave solitons. In fact, what you saw on the surface was a signature of huge waves riding internally. A mile in length, 300 feet in amplitude. That's pretty big. These guys, the surface waves, 6 to 8 feet. They come in groups 4 to 8 every 12, I said 11 hours, 12 hours and 26 minutes. And in length, transversely, they're very, very long, mostly one-dimensional. And they persisted for 250 miles over 2 days. And given the parameters, this was Korteweg de Vries equation. So those guys are giant solitary waves, right probably someplace off of Brazil. This is not just the only place where they observed it, many, many places in the ocean. Here's a diagram of what's going on. Here's your wave, and there's your oil platform, and the waves come from the ripples, and they're the birds, everything. Okay, let me tell you a snapshot of optical communications. Well, if you look at where solitons are most popular today, it's in the field of optics. And field of optics is very interesting, especially communications. You want to send a signal. I mean, everybody just about that flies has a BlackBerry, right? Not me, but pressing their buttons, reading their email. What's going on? It's going from your cell phone or BlackBerry to a satellite, comes down in Brazil here, then it goes undersea by optical fibers to wherever. Suppose you're speaking to somebody in the United States or Japan, goes through underwater cables. Now, if you go to Maxwell's equations, you have a wavelength. That's typically, they send it 1,550 nanometers, okay, 1.5 micrometers. At any rate, it's 10 to the minus 6. And you're going to send it 10,000 kilometers. That's a huge scale difference. And they're both in Maxwell's equations. So to use Maxwell's equations is essentially impossible. Give up, don't try. But happily, for people in optics are mathematicians. They're happy. That's why math is fun. Another reason why. Okay, because you have to reduce Maxwell's equations to something tractable. And the reduction through asymptotic methods is to an equation of this form. Nonlinear Schrodinger type equation. D is called the dispersion, G is damping amplification. Now, if D is 1 and G is 1, this is one of the equations that I listed. And you can go to the books and pour on the theory. Well, back in 1973, Hasegawa and Tappert realized this equation was special, and they proposed solitons for communications. And experiments were done a few years later in the 80s and 90s, and they were really fantastic. But that wasn't the end, because they don't send one signal. Now, what's a signal? It's a soliton is a 1 or a 0. 1, 0, 1, 0. So it's a high-speed telegraph. Nearly light speed. That's why you don't send things through satellites. You send it optics because you're sending everything by light speed. Okay, you don't have any interference with that. Any rate, people realize they can send in one fiber simultaneously many signals. Typically, send about 100 channels. Think of red, green, blue, ... Each frequency centered is a hump. It's essentially can be thought of as a soliton. But there were interactions. And in the 90s, people realized that they move with different velocities. They start interacting. This is not an integrable situation because you had damping and amplification in there. So they caused some serious problems. And people developed what's called dispersion management. And I'm going to tell you just a few words about this because it's used today. And the mathematics is very nice, which I'm not going to get into. Just give you the reference. Dispersion management reduces penalties, and it's commercially used. Every underwater line is dispersion management. And nicely, it has solitons and other solutions, quasi-linear solutions, which are effectively just like solitons. Now, what's dispersion management? Here you are in Brazil, there you are in Japan. You send a signal, and you send it in this line. There's what we call a pre-compensation fiber and a post-compensation fiber. They're very small and can be neglected with reasonable approximation, but you can take it into account if you want. And then you take the fiber and you break it into two pieces, a piece with one dispersion and a piece with another. And for the piece with one dispersion is some length, piece with another is another length, and then the damping and amplification factor goes down, so solitons would decay, then they're pumped up, then they decay, and for reasonable approximation, just can take this to be 1. This guy is more complicated and leads you to the following model. Here's your equation. D is an average plus a very large, rapidly varying function, delta 1 and delta 2. Two different constants with different signs. And this average here is called, this area is called the map strength. And the point is, this is a nonlinear homogenization problem. And people who do asymptotics use method of multiple scales. That's what we used, which we developed this method. And with this, which I'm not going to go through, because it's not quite appropriate here, you can make predictions on multiple channels. Not only can't you do Maxwell's equations, there's no way to solve multiple nonlinear Schrodinger equations that are highly coupled. It's too long. But with the theory that developed here, we can make predictions on any number of channels in times of 10 to the 5th faster than direct numerics. Here is what we call a classical soliton that you saw before, and here's a dispersion managed soliton. So at least I told you about dispersion management. One more application of dispersion management, then zeros and ones. Dispersion management. Well, I'm sitting in my office one day, and this happens. This is the real thing. And I get a phone call from one of the local physicists in Boulder. There's the so-called GILA laboratory, which is a combination of physics and the National Institutes of Standards. And they said, well, they are dealing with ultra-short pulses and lasers. And they thought maybe we could help them because they knew some of our work in dispersion management. And here's their experiment. Take a pump laser, you send in a pulse. You send in a laser pulse. Goes through this crystal called tisapphire crystal, which excites the pulse. Then it goes through a mirror. Then it goes through this prism pair. Goes to another mirror, comes back. And then when it comes back, a little bit is shut off, and you get a pulse. And it goes out millions and millions and millions of times. You get a sequence of pulses. And these are 10 femtosecond pulses. Very short, extremely short. And they can repeat them every 10 nanoseconds. They can repeat them for a long time. Now, what they wanted to understand was whether this was a soliton. Now, why does this relate to dispersion management? Tisapphire crystals are in the normal range. It has negative dispersion. And you can't produce solitons there. So what the experiments figured out is they had to put a prism pair, which gives you positive dispersion. And therefore, you get negative, positive, negative, positive, negative, positive. And it just fit. It's one of those lucky incidences that somebody walks in and tells you something, and once you understand what they're saying, that's not easy. Mathematicians speak one language, physicists speak another, and it takes half the battle is just understanding what they want to tell you. But once you understand it, wow. And so we developed the theory, very similar to communications, and published it, and compared it to experiments. Very, very nice. Very nice. Now, why is the application of interest to them? Well, you've heard about atomic clocks, right? Those are the fancy clocks that keep the time in Brazil. Without them, how would you know what time it is? Same in the United States. They have one group that keeps the time. And they have this big amount of equipment called a fountain clock. And the idea is to take this thing, which is not even as big as this table, which is getting smaller, and to replace the fountain clocks by optical clocks. Optical clocks are more accurate. Every soliton, pick, 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 is a tick on that optical clock. And most people believe that this will outdo atomic clock technology. Now let me go to zeros and ones and we'll be done. Because this is pure math, and it's always nice to do some pure math. And it's fun math. And my daughter helped me. Think of a checkerboard. And in that checkerboard, you either have a 1 or a 0, black or white. And you want to update the checkerboard. Okay, so I have to give you a rule to update the checkerboard. I give you a value here, and I give you a rule for all these guys around it. This is called the neighborhood n. And this is a two-state rule. 0 connotes dead, 1 connotes alive. And the rule, this is called the game of life. And everybody can play it. You just go on the web and look it up. And you can look for things I'm going to tell you about. The rule for life is this. If you will get a 1 at the next checkerboard. T plus 1 means T plus 1, T plus 2. Checkerboards. You'll get a 1 here if this guy was 0 and there's exactly 3 living cells, 3 ones in here. There's a birth. From 0, you birth, you have a birth. You will get a 1, if you start with a 1, if there are 2 or 3 living cells. You'll survive. Otherwise, you're going to die from loneliness or overcrowding. That's the rule. I mean, you can't ask for a simpler rule. This is just magic. First written by Martin Gardner in his column back in the late 60s. But John Conway came up with this. Here's some special solutions. A block, it just stays there. A beehive just stays there. A blinker, this is a beacon. And there's a glider, a little guy that moves. I was giving this lecture, and I had some other things to say about zeros and ones, which I'm not going to say today. I played with them for a while in sort of exotic ways. But somebody said to me, well, you know, have you ever seen these exotic solutions? I said, no. I mean, he said, they're great. You ought to go and try to find them. And there is an exotic guy, okay? What does that look like? Spaceship. It's called a spaceship. To the people who play Game of Life, it's a spaceship. Now, let's see if I can get it to play. Well, you think I opened it? Well, let's go back. Let's go back here. Ah, there you go. That's a solitary wave. If I didn't have it, and I told you about it, you wouldn't appreciate it. Now that you can't do with transparencies. Right? So my daughter went to the web and found this solution. We were great. We were real happy. Now, what does any self-respecting Soliton person do? Stephanie was by that time a self-respecting Soliton person. So she interacted them. What do you think happens? Is it a Soliton in the elastic sense? No. But it sure is pretty. I'll do it once more, and then we're done. So that's what I call math is fun. After all, why do math? We also developed, by the way, from zeros and ones, an encryption algorithm, which we patented, and nicely enough, it was even licensed, shockingly. My reasoning for that is that they licensed it because they didn't want any competing technology. But at any rate, here's the conclusions. I gave you a historical discussion. John Scott Russell, his so-called wave of translation, or solitary wave, where solitons come from, how do they relate to eigenvalues of an underlying linear operator, an inverse problem, tell you a word or two about it, Riemann-Hilbert, or D-bar, I really didn't say much. They're important in water waves, optics, internal ocean waves, and then I have a few words about zeros and ones. And that is it.
So in the game of life, being loneliness and solitary are not quite the same thing, right?
Yeah, that's true.
Okay. So, question, perguntas, comentários para o professor Ablowitz?
Yes.
They work with, they generalize the Soliton Sine-God equation and have the Backlund generalized Backlund theorem. There is a generalization of the inverse scattering for many dimensions, and they found any equation.
Yes. So I too studied some problems in multi-dimensions, but I say 3 plus 1, if you really look at these papers, it's better to say it's like 1 plus 1 plus 1 plus 1. To properly pose it, you have to pose it only along one line, not along, a plane for 3 plus 1 dimensional problems. So that's why I made a distinction. Yes, there are formally multidimensional problems. Any hierarchy can be viewed as a multidimensional problem, but not as a 3 plus 1 dimensional problem in the sense I'm talking about. But if you can convince me that it's 3 plus 1, then I'll change that slide. Yes.
In the internal wave example, what is the depth of each layer? I couldn't write.
Yes. So in the internal waves, those figures I took were about 3,000 miles. And the depth, the full depth. The soliton was 300 feet in amplitude, but the full depth was 3,000 miles, I think. But the waves are very long, maybe 3,000 feet. Yeah, 3,000 meters. 3,000 meters. Yeah, I'm off by from meters to miles. But the wavelength that sets it off is longer than both depths. That's why KDV comes out. It's not deep water. It's considered to be moderate depth.
So it's more or less half an inch.
No, the top is smaller than the bottom. The top is about a fifth, as I recall, the full depth, the top piece. So you have a warm layer, cold layer. So this is 1, this is the whole thing would be about 5, as I recall. And it's a soliton that goes down into the deeper water. But this was also published in 1980 by Osborne and Birch. And it was the first observation and science, and subsequently it's just a big area of research. In many areas off the coast of the US for sure, and in Indonesia, and how could it not be off the coast of Brazil? It's got a big coast.
Perguntas, comentários?
It's not complete by any means. There's so many more of physical significance. I picked out my favorites. So I picked out not only Schrödinger because it comes out of optics, Sine-Gordon is one of my favorites, 3-wave, KP, which I talked a little bit about, Benjamin Ono. But there's many, many more. What is your favorite? And the elliptic version of Sine-Gordon, which has deep implications to geometry, of course. But I'm an evolution guy, a waves guy, so I had to keep myself into the evolution front. But you're absolutely right. There are many others. There's the Thuring model. There's the derivative non-Schrödinger equation. There's the total lattice. I could just keep on going, but I'd bore everybody. You throw me off the stage. Now I've been here too long, probably.
One more question?
Yes. You know I like to teach, right? Which doesn't help me, by the way.
In 1 + 1 dimension, the inverse scattering method serves really to, at least for some equations, to fully solve the general Cauchy problem. How is the status of this? Not just the question of specific solutions in the case of the KP.
That's a good question. For decaying data, it's in, I would say, certainly not as good shape as 1 + 1 rigorously, but the method is there, and the method gives you eigenvalues, it gives you scattering data, you have the integral equations, you can show that the solutions you get satisfy the equation. I think Wickerhauser has a reasonable theory for the direct side. The inverse problem, I'm not sure whether there's a complete theory for the inverse problem that matches the decay. Part of the problem is these solitons decay and they're not L1. They have weak decay. So I'm not sure there's a convenient inverse theory that will get you the solitons.
Okay, so let's thank Professor Ablowitz once more.